13.8 billion years ago, the universe began. In one moment, there was nothing, and the next, there was everything. This instant transformation, this sudden birth of space, time, energy, and matter challenges the boundaries of our understanding. How could everything we know, the stars, galaxies, light, and even the laws of physics, emerge from nothingness? This question lies at the heart of cosmology, and it's more than just a scientific puzzle. It's a philosophical and existential enigma. Everything we comprehend about reality is rooted in causality, the idea that every effect must have a cause. Yet here we are, trying to explain the ultimate event, the beginning of all things. What triggered the universe into existence? This lack of explanation doesn't stem from a lack of curiosity. Scientists, philosophers, and thinkers have long wrestled with this mystery. One possible resolution comes from Stephen Hawking, who suggested that asking what came before the Big Bang is as meaningless as asking what is north of the North Pole. In his model, time and space are interwoven properties of the universe, and both sprang into being at the Big Bang. There was no before, because time itself didn't exist. Others argue that our inability to see beyond the Big Bang is simply a limitation of our instruments and theories, a horizon in our knowledge. What if there is a realm beyond our observable universe? A landscape of countless other universes, each with their own beginnings, physics, and timelines. This brings us to the theory of inflation, the idea that a split second of exponential expansion propelled the universe into being. Inflation explains why the universe appears so smooth and flat, and why it looks the same in all directions. But it also opens the door to something even more extraordinary: eternal inflation. According to this model, inflation never completely ends. Instead, it spawns countless pocket universes, each with its own Big Bang. Our universe would just be one bubble in a vast multiverse. So what was the spark? Was there a quantum fluctuation in a pre-existing field that ignited inflation? Or does the answer lie in a theory we haven't discovered yet, one that unifies quantum mechanics and general relativity? Until we have a theory of quantum gravity, we can only speculate. Still, the very idea that time had a beginning forces us to rethink our assumptions. Time is so central to our daily experience. We measure it, we live by it, we age because of it. Yet the universe itself may have emerged from a timeless state. What does it even mean for something to exist outside of time? In this timeless state, the laws of physics as we know them might not apply. Cause and effect might be meaningless. Concepts like before and after might simply not exist. It's possible that what we perceive as the beginning is just a transition from one phase of reality to another, a bounce, a cycle, or a transformation. The universe might have been born not from nothing, but from something entirely different from what we understand. A quantum void teeming with potential, or a higher dimensional space beyond our comprehension. The truth might be even stranger than our wildest theories. We are still at the frontier of this mystery. The more we learn about the early universe, through cosmic microwave background radiation, gravitational waves, and particle physics, the more questions arise. Every answer reveals deeper layers of the unknown. One thing is certain: the story of the universe's origin is not just about astrophysics. It's about who we are, where we come from, and the limits of human understanding. In seeking the beginning, we are ultimately searching for ourselves in the cosmos. Stay tuned, because in the next segment, we'll explore the incredible theories of inflation, multiverses, and what they mean for the future of science. Subscribe to Infinity Beyond, and let's continue this mind-expanding journey together. In our journey to uncover the origin of everything, we arrive at one of the most intriguing ideas in modern cosmology: cosmic inflation. This theory proposes that in the tiniest fraction of a second after the Big Bang, the universe underwent a sudden, exponential expansion, growing from subatomic to galactic scale faster than the blink of an eye. But why did this happen? And what does it tell us about where we came from? Inflation is not just a convenient theory. It solves several deep puzzles in cosmology. For instance, why is the universe so incredibly smooth and uniform across vast distances? Why does it appear flat rather than curved or warped? And why is there no observable magnetic monopole, a particle predicted by grand unified theories? According to inflation theory, the entire observable universe originated from a tiny, causally connected patch of space. When inflation occurred, that patch stretched so rapidly that it smoothed out any irregularities, explaining the cosmic microwave background's uniformity we observe today. In short, inflation provided the cosmic ironing out necessary for the universe to evolve into what we see. But inflation also opened up the gates to one of the most radical ideas in physics: the multiverse. The theory of eternal inflation suggests that inflation doesn't stop everywhere at once. Instead, it ends in some regions but continues indefinitely in others, creating a constantly branching structure of pocket universes, each with its own version of physical laws, constants, and maybe even dimensions. This is the multiverse. In our universe, inflation ended after a fraction of a second, allowing matter, galaxies, and stars to form. But elsewhere, in other regions far beyond our observable horizon, inflation could still be occurring. New universes could be born every moment, each igniting its own Big Bang. If true, this changes everything. It means our universe might be just one leaf in an ever-growing cosmic forest. The fundamental constants of nature, the charge of the electron, the strength of gravity, the rate of cosmic expansion, could be different in each universe. Some might be lifeless, while others may harbor forms of life unimaginable to us. And what about us? Why do we live in a universe perfectly tuned for life? The anthropic principle suggests that we observe these precise conditions because only in such a universe could observers like us evolve. In other words, it's not that our universe is special, it's just that we're here to notice it. This might sound like science fiction, but it's supported by real mathematics and quantum field theory. The vacuum energy of space, a field with inherent quantum fluctuations, can create regions where inflation kicks off. These bubbles grow into new universes, forming a cosmic foam stretching beyond imagination. Yet, inflation is not without its challenges. For one, it's difficult to test directly. Much of the evidence for inflation comes from indirect observations, such as the detailed patterns in the cosmic microwave background or the distribution of galaxies across the sky. But scientists are pushing the boundaries, seeking evidence in gravitational waves, primordial B-modes, and high-energy particle physics. Still, some physicists question whether inflation is the final answer. They propose alternative theories, like bouncing cosmologies, where the universe didn't begin with a bang, but rebounded from a previous contracting state. Others invoke string theory, where tiny vibrating strings form the basis of matter, and extra dimensions could hold the key to everything. The deeper we look, the stranger the answers become. The beginning of our universe might not be a singular event, but part of a timeless process, a cosmic cycle of birth, death, and rebirth on scales far beyond comprehension. And yet, even within our tiny corner of the multiverse, incredible things have happened. Out of swirling gases and gravitational chaos, stars ignited, planets formed, and life emerged. All because inflation gave the cosmos the right conditions to thrive. As we contemplate the vastness of this inflationary multiverse, we must also reflect on what it means to be conscious beings within it. If we are just one of countless possibilities, how do we find meaning? If universes are born and die endlessly, What is the significance of our fleeting existence? Maybe the answer lies not in diminishing our value, but in expanding our perspective. To understand that we are part of a grand, unfolding story, one that stretches across dimensions and realities, and to find wonder in the fact that we can ask these questions at all. So the next time you look up at the night sky, remember, behind those stars might lie gateways to infinite worlds. Worlds where physics takes a different path, where light bends in impossible ways, where perhaps other versions of us gaze into their own skies and wonder the same. At Infinity Beyond, we believe that exploring these frontiers isn't just science, it's a celebration of curiosity. And the more we learn about the universe, the more we learn about ourselves. Don't miss our next episode, where we delve into the mysterious concept of time, what it is, how it flows, and whether it's even real. Subscribe and continue this extraordinary adventure with us. Vu Tru Ma, what is time? Is it a constant flow, ticking away from the past into the future? Or is it something far more mysterious, perhaps even an illusion? At first glance, time seems simple. We experience it every moment. We measure it with clocks. We age. We plan. We remember. Time feels like the backdrop of our lives, moving in one direction, forward. But when we look deeper, especially through the lens of physics, our intuitive understanding of time begins to fall apart. Einstein's theory of relativity revolutionized our perception of time. According to general relativity, time is not an absolute universal flow that ticks the same for everyone. Instead, it is relative. It can stretch and compress depending on your speed and the strength of gravity around you. This means that two observers moving at different speeds or experiencing different gravitational forces will measure the passage of time differently. A clock on Earth ticks at a slightly different rate than one on a satellite in orbit. This is not just theory. It's a real effect we have to correct for in GPS satellites. Time, it turns out, is a dimension, much like space. Together, they form what we call space-time. And in this four-dimensional fabric, the future, present, and past may all coexist, just like all locations in space exist at once. So, if time is a dimension, does that mean the future is already there? Are we simply experiencing one slice of the temporal loaf at a time? This idea is known as the block universe theory, where the universe is like a frozen 4D structure, and the passage of time is just an illusion born from our consciousness moving through it. But then, why do we experience time as flowing? Why do we remember the past, but not the future? This brings us to the concept of entropy, the measure of disorder. According to the second law of thermodynamics, entropy tends to increase over time. This increase gives time its apparent direction, what physicists call the arrow of time. In a low entropy state, like the early universe, structures and patterns were simple and organized. As time progresses, systems move toward higher entropy, toward disorder. Ice melts, eggs break, stars burn out. These processes are irreversible and help define the flow of time. But here's the twist. The laws of physics are time-symmetric. They don't distinguish between past and future. So why does time have a preferred direction for us? Some scientists suggest that the arrow of time is tied to the initial conditions of the universe. The Big Bang began in a state of extraordinarily low entropy. From that moment, entropy could only increase. If the universe had begun in a high entropy state, the arrow of time might not exist, or might point in a different direction. Others wonder if time is even fundamental at all. In certain approaches to quantum gravity, like loop quantum gravity, time does not appear as a basic ingredient. Instead, it may be an emergent property, arising only when many particles interact. In these models, time is not a thread running through the fabric of reality, but a statistical byproduct of more fundamental processes. It would be like temperature. something that emerges from the collective behavior of molecules, not something that exists on its own. This opens up wild possibilities. If time is emergent, then perhaps in some corners of the universe, or in other universes entirely, time as we know it does not exist. What would existence be like without time? Could consciousness still arise? And what about time travel? If the block universe is correct, and all moments in time exist simultaneously, then traveling through time might be as natural as traveling through space. But paradoxes arise. Can you change the past? Could you meet your future self? Some solutions come from Einstein's equations themselves, such as wormholes or closed time-like curves. These hypothetical constructs would allow paths through space-time that loop back on themselves. In theory, they permit time travel. In practice, they remain speculative, and no evidence of such structures has yet been found. Quantum mechanics adds yet another layer of mystery. In the quantum world, particles don't evolve smoothly over time, but exist in a superposition of states until observed. Some interpretations, like the transactional interpretation, suggest that events in the future can influence the past, creating a kind of retrocausality. If true, our notion of time as a one-way street would need a major overhaul. At Infinity Beyond, we ponder not just what time is, but how it defines us. We are time-bound beings. Our thoughts, decisions, hopes, and regrets are all woven into the fabric of time. And yet, the more we study it, the more it seems like a construct, a phenomenon that arises from deeper rules we don't yet fully understand. Time affects everything, from how we perceive the cosmos to how we experience love, loss, growth, and death. Without time, there would be no stories, no change, no history. But perhaps, in some higher realm, all stories are already written, and all moments already exist, waiting to be experienced. In our next episode, we'll move from time to structure, investigating how matter clumped into stars, galaxies, and the vast cosmic web that stretches across the universe. If you've ever wondered what time truly is, and whether it's real, you're not alone. Subscribe to Infinity Beyond, and let's continue questioning everything. Ta biết ngày nay bắt đầu từ một khoảnh khắc kỳ diệu, một vụ nổ vũ trụ rực rỡ từ khoảng không vô tận, mở ra không gian, thời gian và mọi vật chất. Từ bóng tối tuyệt đối, ánh sáng đầu tiên lóe lên, những hạt vật chất sơ khai hòa quyện, tạo nên các ngôi sao, thiên hà và hành tinh. Đó là khởi nguồn của tất cả, nơi vô hạn vượt xa mọi giới hạn, dẫn dắt nhân loại khám phá bí ẩn của sự tồn tại. The universe, though vast and seemingly chaotic, is built on an intricate structure, a cosmic web that spans billions of light years, shaping galaxies, stars, and ultimately, life itself. But how did this structure form from the aftermath of the Big Bang? It all began with tiny fluctuations, microscopic variations in density. So small they were mere 1 in 100,000 differences in the early universe. These fluctuations are preserved in the cosmic microwave background, CMB, a faint afterglow of the Big Bang that fills the entire sky. Like fingerprints frozen in time, they offer a snapshot of the baby universe. These quantum fluctuations, stretched to cosmic scales by inflation, acted as seeds for everything we see today. Gravity took hold of these denser regions, drawing in more matter and amplifying their growth. Over billions of years, these slight overdensities became galaxies, clusters, and the immense filaments of the cosmic web. The cosmic web is not a metaphor. It's a literal structure. Simulations and deep space surveys reveal a network of interconnected filaments made of dark matter and gas, with galaxies forming along these strands like dewdrops on a spider's thread. These filaments intersect at nodes called galaxy clusters, the densest, most massive structures in the known universe. In between these filaments lie vast cosmic voids, immense, empty regions with almost no matter. These voids are just as important as the filaments. They help define the geometry of the web. Think of it like a sponge, full of holes and tunnels, only on a scale of hundreds of millions of light-years. Dark matter plays a crucial role in shaping this structure. Although invisible, it makes up about 85% of the total matter in the universe. It interacts gravitationally, guiding the formation of galaxies and binding them together. Without dark matter, the structures we see wouldn't exist. But dark matter alone isn't enough. Baryonic matter, the kind we're made of, follows the blueprint laid out by dark matter. After recombination, when the universe cooled enough for neutral atoms to form, baryonic gas began to collapse into the gravitational cells created by dark matter. Over time, these regions became hot, dense, and luminous, birthing stars, galaxies, and planets. Star formation ignited feedback loops. Exploding supernovae enriched the interstellar medium with heavier elements, while black holes at the centers of galaxies stirred and shaped their hosts. These processes turned the raw ingredients of the cosmos into complex systems. But it didn't happen all at once. Structure formation is a hierarchical process. Small galaxies formed first and merged into larger ones. Galaxy clusters formed later, accumulating mass over billions of years. Even today, galaxies are still colliding, still growing, still evolving. Telescopes like the Sloan Digital Sky Survey and the Dark Energy Survey have mapped millions of galaxies, revealing the skeleton of the universe. Their data confirms what simulations like the Millennium Run predicted: a fractal-like distribution of matter on the largest scales, governed by physics, randomness, and the initial conditions of the cosmos. Interestingly, this large-scale structure tells us more than just where things are. It also holds clues about what the universe is made of and how it's evolving. By studying the distribution of galaxies, cosmologists can measure the effects of dark energy, the mysterious force accelerating the expansion of the universe. Ripples in the matter distribution, known as baryon acoustic oscillations, serve as cosmic rulers, allowing us to trace the history of expansion. These sound waves from the early universe left imprints in the density of galaxies, and they act like a yardstick across space and time. And here's a profound thought: the very atoms in your body were once part of those ancient waves. The calcium in your bones, the iron in your blood, all originated from stars that formed along these filaments, which themselves formed from fluctuations in the primordial soup. You are, quite literally, a child of the cosmic web. This perspective transforms our sense of identity. We are not isolated observers. We are products of cosmic processes that began nearly 14 billion years ago. Our bodies, our planet, even our thoughts, all shaped by the hidden architecture of the universe. And we are still learning. Upcoming telescopes like the Euclid mission and the Vera C. Rubin Observatory will map the universe in unprecedented detail. They'll peer deeper into space and further back in time, allowing us to refine our understanding of structure formation. New computer simulations, powered by artificial intelligence, will model the evolution of cosmic structures across billions of years with astonishing precision. Some theorists even propose that the cosmic web might influence consciousness, that the large-scale connectivity of the universe echoes the structure of neural networks. Though speculative, such ideas point to a growing recognition of the deep, perhaps poetic resonance between cosmos and consciousness. At Infinity Beyond, we explore these vast themes not just for science, but for meaning. The universe is not just a place. It's a story, and we're part of its unfolding narrative. In our next segment, we'll leave the large-scale structure behind and dive into one of the most mysterious forces shaping that structure: dark energy. What is it, and why is it pulling the cosmos apart? Subscribe and stay with us on this remarkable journey across time, space, and structure. In the late 1990s, something extraordinary happened in the world of cosmology. Two independent teams of astronomers studying distant supernovae made a shocking discovery. The expansion of the universe isn't slowing down, as previously thought. It's speeding up. This observation defied expectations. For decades, scientists believed that gravity would eventually slow the cosmic expansion, perhaps even causing a big crunch, a reversal back into a singularity. But instead, something unseen, something mysterious, was accelerating the universe outward at an ever-increasing rate. They named it dark energy. This term sounds simple, but don't let it fool you. Dark energy is not well understood. In fact, it's arguably the most profound mystery in modern physics. It accounts for nearly 78% of the entire energy content of the universe, yet we don't know what it is, where it comes from, or why it exists. So what could this elusive force be? The leading theory suggests that dark energy is an intrinsic property of space itself, the vacuum energy. In quantum field theory, even empty space is teeming with virtual particles that pop in and out of existence. These fluctuations may contribute a tiny but pervasive energy that exerts a repulsive force, causing space to expand. Einstein once introduced a concept called the cosmological constant, a fudge factor in his equations to maintain a static universe. He later called it his biggest blunder after Hubble's discovery of cosmic expansion. But now, that cosmological constant may be the very key to understanding dark energy. If the vacuum of space holds energy, and that energy has a repulsive effect, then as the universe expands, more space means more vacuum energy, which in turn accelerates the expansion even more. It's a feedback loop on a cosmic scale. However, there's a problem. When physicists try to calculate the energy of the vacuum using quantum mechanics, they get a value that is 120 times larger than what is observed. That's a number so massive, it's considered the most wrong prediction in the history of science. Clearly, something is missing from our understanding. Some scientists propose that dark energy isn't constant at all, but dynamic, evolving over time. This idea is called quintessence, a term borrowed from ancient philosophy. In this model, dark energy is a field that changes in strength depending on the conditions of the universe, similar to how inflation operated in the early moments after the Big Bang. Others believe that what we call dark energy may simply reflect our incomplete knowledge of gravity itself. Maybe Einstein's equations need tweaking at cosmic scales. Modified gravity theories, such as FER gravity or extra-dimensional models, attempt to explain cosmic acceleration without invoking mysterious energy. There's also the possibility that dark energy is tied to the geometry of the universe. If the cosmos has a shape we haven't fully grasped, one involving curvature or higher dimensions, then what appears as acceleration might be an illusion caused by our limited perspective. Regardless of its origin, dark energy is powerful. It's not only pushing galaxies away from each other, but it's also changing the fate of the universe. If dark energy remains constant or increases, the cosmos will continue expanding forever, growing colder, darker, and emptier in a scenario known as the Big Freeze. In even more extreme models, dark energy could grow stronger over time. In this Big Rip scenario, galaxies would eventually be torn apart, stars pulled from their orbits, planets shredded, and even atoms themselves ripped to pieces. Space would stretch so violently that nothing could hold together. But we're not there yet. For now, astronomers use Type Ia supernovae, exploding white dwarf stars, as cosmic yardsticks to measure dark energy's effects. They also analyze the cosmic microwave background, the distribution of galaxies, and gravitational lensing to refine their models. Future observatories like the Euclid Space Telescope and the Nancy Grace Roman Space Telescope aim to map the universe with unprecedented precision. By surveying billions of galaxies, they will help determine whether dark energy is truly constant or if it's evolving over time. The answers they find could rewrite the laws of physics and reshape our understanding of reality itself. And here's the most fascinating part. Without dark energy, life as we know it might not even be possible. If the expansion of the universe had been too slow, matter would have clumped too quickly, forming massive black holes or collapsing into a dense, hot soup. Too fast, and galaxies would never have formed. Somehow, dark energy has exactly the right value, not too strong, not too weak, to allow stars, planets, and eventually life to emerge. This uncanny fine-tuning has led some to suggest a multiverse explanation where countless universes exist with different values of dark energy. We just happen to live in one where conditions are just right for observers like us to ask the question, why? Whether it's a constant, a field, a geometry, or something entirely new, dark energy is a reminder of how much we still don't know. The cosmos is still revealing its secrets, and every answer leads to deeper questions. At Wantin, Infinity Beyond, we're committed to exploring these profound mysteries, not just for knowledge, but for perspective. Dark energy is more than a force. It's a cosmic invitation to look beyond what we see and imagine what might lie beneath the surface. In the next segment, we'll shift our focus to dark energy's mysterious counterpart, dark matter, the invisible scaffolding that holds the universe together. Subscribe to WAM Infinity Beyond, and let's continue unraveling the invisible forces that shape reality. If dark energy is the force pushing the universe apart, then its cosmic counterpart, dark matter, is the force holding it all together. Though we cannot see it, touch it, or detect it directly, dark matter makes up about 27% of the universe. That's more than 5 times the amount of regular matter, the atoms that make up stars, planets, and everything we know. Yet it remains one of the greatest unsolved mysteries in physics. So how do we know it exists? The evidence for dark matter is overwhelming and comes from multiple cosmic clues. One of the first signs came from observing the rotation curves of galaxies. According to Newtonian mechanics, stars farther from a galaxy's center should orbit more slowly, just as planets in our solar system do. But when astronomers like Vera Rubin measured galactic rotation, they found that stars on the outskirts were moving just as fast as those near the center. This could only be explained if there was something invisible, some unseen mass, adding to the galaxy's gravitational pull. And not just a little. In most galaxies, dark matter outweighs normal matter by a factor of 5 or more. Similar evidence comes from gravitational lensing, where the light from distant galaxies is bent as it passes massive objects. The amount of bending reveals the mass of the object causing it, and in many cases, there's far more mass than what we can see. That extra mass is attributed to dark matter. We also see its effects in galaxy clusters, cosmic microwave background fluctuations, and the large-scale structure of the universe. Without dark matter, galaxies wouldn't have formed the way they did, or perhaps at all. But what is dark matter made of? That's the trillion-dollar question. The leading candidates are theoretical particles that rarely interact with ordinary matter. These include WIMPs, weakly interacting massive particles. Heavy, slow-moving particles predicted by some extensions of the Standard Model. They barely interact, except through gravity. Axions. Lightweight particles proposed to solve problems in quantum chromodynamics. Though incredibly light, axions could be produced in enormous numbers, making up a large dark matter component. Sterile neutrinos. Hypothetical heavier versions of the neutrino that don't interact via the weak force. If they exist, they could explain several anomalies in particle physics. Despite decades of searching, none of these particles have been directly detected. Massive underground detectors, buried deep beneath mountains or ice, attempt to catch the rare interaction of a dark matter particle with a normal atom. So far, the results have come up empty, but the search continues. Some researchers have proposed alternative explanations, like modifying gravity itself. The MOND theory, modified Newtonian dynamics, suggests that gravity behaves differently on galactic scales, potentially removing the need for dark matter. However, while MOND can explain galaxy rotation curves, it struggles with other observations, such as cluster behavior and the cosmic web. There are also more exotic ideas. What if dark matter is made of primordial black holes formed in the first moments after the Big Bang? Or what if it's part of an entire dark sector, a parallel set of particles and forces that don't interact with ours, except gravitationally? Some even suggest that dark matter could carry its own dark electromagnetism, with dark photons and dark atoms forming structures like our own, but invisible. In that scenario, there could be dark galaxies, dark stars, maybe even dark life. It's pure speculation for now, but tantalizing. Whatever it is, dark matter is not just passive scaffolding. It shaped the universe's structure, pulled gas into halos, helped galaxies form, and holds them together even today. Without it, the Milky Way would fly apart. Simulations of cosmic structure, such as the Millennium simulation, show that dark matter forms vast halos around galaxies, connecting them into filaments and clusters. These halos act like gravitational wells, anchoring luminous matter and guiding the evolution of the cosmos. Even the Earth orbits within one such halo. Our entire solar system is immersed in dark matter, passing through it without interaction, like ghosts through fog. Could dark matter be detected in the future? Possibly. The Large Hadron Collider and upcoming high-energy experiments continue to search for clues. Next-generation detectors like Lux Zeppelin and a Xenon NT are pushing the boundaries of sensitivity. Space missions like the upcoming Euclid and the Vera C. Rubin Observatory may provide indirect evidence by mapping dark matter's gravitational effects with even greater precision. And if dark matter is part of a larger hidden framework, a new sector of physics, it could change everything we know about the Standard Model, cosmology, and even the origin of mass itself. At Infinity Beyond, we believe this is more than just science. It's a story of mystery, persistence, and imagination. Dark matter challenges us to think beyond the visible, to question what reality really is, and to keep searching even when answers seem just out of reach. In the next segment, we'll journey into one of the most extreme and fascinating phenomena in the universe, black holes, where gravity reigns supreme and even time itself breaks down. Subscribe now to Infinity Beyond, and let's continue decoding the dark. Among the most mysterious and awe-inspiring objects in the cosmos are those black holes, regions of space where gravity is so intense that nothing, not even light, can escape. They are cosmic enigmas, distorting space, time, and the laws of physics themselves. But what exactly is a black hole? And how do they form? A black hole is created when a massive star runs out of nuclear fuel and collapses under its own gravity. If the remaining mass after a supernova explosion is dense enough, it will compress into an infinitesimally small point called a singularity, surrounded by a boundary known as the converge event horizon, the point of no return. Inside this region, the escape velocity exceeds the speed of light. That means even photons, particles of light, cannot escape its grasp. Hence, they appear completely black. But black holes aren't just empty voids. They are incredibly dense, containing immense mass in a tiny volume. A black hole the size of a city block can weigh more than our sun. and the gravitational influence they exert can stretch across entire solar systems. Black holes come in different sizes. Stellar black holes form from dying stars and usually contain a few solar masses. Intermediate black holes, weighing hundreds to thousands of solar masses, are harder to detect but believed to form in dense star clusters. Supermassive black holes, millions to billions of times the Sun's mass, sit at the centers of most galaxies, including our own Milky Way. In fact, at the core of the Milky Way lies Sagittarius A, a supermassive black hole about 4 million times the mass of the Sun. It's surrounded by stars that whip around it at incredible speeds, revealing its presence through their motion. But how do black holes interact with the universe around them? Despite their ominous reputation, black holes don't suck things in like cosmic vacuum cleaners. Instead, objects must cross the event horizon to be lost forever. Outside that boundary, they influence matter gravitationally, just like any other massive object. However, when matter falls into a black hole, it forms an accretion disk, a swirling ring of superheated gas and dust that spirals inward, glowing with intense radiation. These disks can shine brighter than entire galaxies, especially when feeding rapidly. Such black holes are called quasars. In 2019, scientists captured the first-ever image of a black hole's event horizon using the Event Horizon Telescope, a global array of radio telescopes working together. The blurry orange ring surrounding darkness wasn't just a scientific milestone, it was humanity's first direct glimpse of the shadow of a black hole. And that's just the beginning. Black holes also merge. When two black holes collide, they produce gravitational waves, ripples in space-time, predicted by Einstein and first detected by LIGO in 2015. These waves carry information about the most violent events in the cosmos and open a new window for observing the universe. But the mysteries go deeper. Inside the event horizon, general relativity predicts that all matter collapses into a point of infinite density, the singularity. However, at these scales, quantum effects become significant, and our current theories break down. Physicists believe a unified theory of quantum gravity is needed to describe what truly happens inside a black hole. Could it be a portal to another universe? A link to a wormhole? A place where time flows backward? These ideas remain speculative, but fascinating. Stephen Hawking added another twist with his discovery of all-Hawking radiation. According to quantum theory, black holes are not entirely black. They emit tiny amounts of thermal radiation due to quantum fluctuations near the event horizon. Over incredibly long timescales, this radiation could cause black holes to slowly evaporate and disappear. But this leads to the Young information paradox, a major puzzle in modern physics. If black holes evaporate completely, what happens to the information they swallowed? According to quantum mechanics, information cannot be destroyed. Yet black holes seem to do just that. Resolving this paradox could reveal deep truths about the nature of reality, time, and space itself. Some researchers suggest that information is stored in a holographic skin around the event horizon. Others believe it's encoded in the Hawking radiation itself. And a few propose that black holes don't destroy information. They just scramble it in ways we don't yet understand. Black holes also challenge our intuition about time. As you approach a black hole, time slows down relative to a distant observer. At the event horizon, time appears to freeze. This isn't science fiction. It's a consequence of Einstein's theory of relativity. In a way, black holes are like cosmic laboratories, places where gravity becomes extreme, where the known laws of physics collide with the unknown, and where new theories are born. At Infinity Beyond, we believe black holes aren't just astrophysical objects. They're keys to the deepest secrets of the universe. In our next episode, we'll explore something even more mind-bending: wormholes and the possibility of interstellar shortcuts. Could black holes actually lead us to other parts of the cosmos, or other universes entirely? Stay curious and subscribe to Infinity Beyond as we journey into the darkest corners of the universe. Imagine stepping into a spacecraft and, instead of spending thousands of years traveling to a distant star system, you pass through a tunnel, a wormhole, and arrive instantly. It sounds like science fiction, but wormholes are a real possibility in the equations of physics. Wormholes, also known as Einstein-Rosen bridges, are hypothetical tunnels that connect two different points in space and time. In theory, they could allow for faster-than-light travel, not by breaking the speed of light, but by shortening the distance between two regions of space-time. The concept dates back to 1935, when Albert Einstein and Nathan Rosen first proposed a mathematical bridge between two black holes. This shortcut through space-time came to be known as a wormhole because it resembled a tunnel. A worm might burrow through an apple, taking a shorter path through the core rather than around the surface. So are wormholes real? In theory, yes. Solutions to Einstein's general relativity equations do allow for wormhole geometries. But the big question is whether they can be traversable, meaning safe and stable enough for something or someone to pass through. Unfortunately, ordinary matter can't keep a wormhole open. Gravity would cause it to collapse almost instantly. To hold a wormhole open, you'd need exotic matter, material with negative energy density and negative pressure. This kind of matter violates the known energy conditions in physics and hasn't been observed in the real world. Yet quantum physics hints that exotic matter might exist. In phenomena like the Casimir effect, quantum fluctuations can produce negative energy in tiny regions of space. Could this principle, on a much larger scale, allow a wormhole to remain stable? Some physicists believe it's possible, at least theoretically. Traversable wormholes could connect distant parts of the universe, or even different times. In that case, they wouldn't just be spatial shortcuts, but time machines, allowing one end to lead to the past and the other to the future. This opens up paradoxes and puzzles that challenge our understanding of causality. For example, what happens if you go back in time and prevent your own birth? The infamous grandfather paradox arises. Does the universe forbid such actions, or does it allow multiple timelines to coexist? One proposed solution is the Novikov self-consistency principle, which says events inside a time loop must be consistent, meaning whatever you do in the past was always part of the past. Others suggest the many worlds interpretation, where traveling through time spawns a new parallel universe. Wormholes could also be connections between separate universes in a multiverse. In such a model, a wormhole might link our universe to a completely different one with its own physical laws, dimensions, and histories. If true, wormholes wouldn't just be shortcuts. They'd be all gateways to entirely new realms of existence. But despite the elegance of these theories, we've never observed a wormhole. They remain hypothetical, existing only in mathematics and imagination. That hasn't stopped scientists from exploring the possibilities. Some researchers believe that certain types of black holes, such as rotating or charged black holes, might contain wormhole-like structures at their core. Others have proposed that if tiny wormholes were created in the early universe, they might still exist, scattered across space at microscopic scales. There's also the idea of constructing a wormhole, using advanced technology and exotic matter. Though far beyond our current capabilities, such engineering would require a mastery of quantum gravity, space-time manipulation, and energy sources we don't yet possess. And then there's the question: would traveling through a wormhole be survivable? The tidal forces near the throat of a wormhole could stretch or compress matter to extreme degrees, potentially tearing apart anything that enters. However, if the wormhole is large and stable enough, and if exotic matter properly lines the walls, the trip might be smooth and safe. Wormholes also provide an intriguing tool for exploring the holographic principle. The idea that the universe's information might be stored on a lower dimensional boundary. In recent studies, some physicists have proposed that quantum entanglement and wormholes are connected, that entangled particles may be linked by tiny wormholes, forming a kind of cosmic network. This concept, known as EPR, named after Einstein-Rosen and Einstein-Podolsky-Rosen entanglement, suggests that space-time itself might emerge from entanglement. In other words, the very fabric of the universe could be stitched together by countless microscopic wormholes. If true, this could revolutionize our understanding of quantum gravity, space-time, and even consciousness. At Infinity Beyond, we don't just chase facts. We explore the boundaries of imagination grounded in science. Wormholes may not be travel routes yet, but they are portals of thought, pushing us to consider what's possible when we stop thinking in straight lines. In our next episode, we'll dive into one of the most mind-altering possibilities of all, the simulation hypothesis. Are we living in a programmed universe? Subscribe now to Infinity Beyond and let your imagination travel farther than light. What if everything you see, the stars, the Earth, even your own thoughts, are part of a massive, sophisticated illusion? The simulation hypothesis suggests just that. Our reality might be an elaborate digital simulation created by an advanced intelligence. It's an idea that has leapt from science fiction into scientific and philosophical debate, raising profound questions about the nature of existence. At first glance, it sounds absurd, something straight out of The Matrix. But when you look deeper, the lines between science and fiction begin to blur. The modern version of the idea was popularized by philosopher Nick Bostrom in the early 2000s. His argument is statistical, logical, and unsettling. Bostrom proposes that one of the following three statements must be true. 1. No civilization will ever reach a level of technological maturity capable of creating simulated realities. 2. If such civilizations do exist, they will not run a significant number of simulations of their evolutionary history. 3. We are almost certainly living in a simulation. Let that sink in. If future civilizations develop the computing power to simulate entire universes, complete with conscious beings, and if they choose to do so even once, then the number of simulated realities would far outweigh the number of real ones. Statistically, it becomes far more likely that we are in a simulation than not. But could a computer really simulate an entire universe? In principle, yes, especially if it's only simulating what we observe. Like in a video game, the environment doesn't render everything at once, only the parts the player is looking at. Similarly, our universe might only be rendered at high resolution where and when it's being observed. This could even explain some of the strangeness of quantum mechanics. In the double-slit experiment, particles behave differently when observed, as if the universe knows it's being watched. Some interpret this as evidence of a programmed reality that saves processing power by collapsing probabilities only when necessary. Even constants of nature, like the speed of light, Planck's constant, or the gravitational constant, could be seen as coding rules set by the simulation's creator. But who or what would create such a simulation? Possibilities range from post-human civilizations to hyper-advanced alien intelligences, entities millions or billions of years ahead of us. If we assume exponential technological growth, It's not hard to imagine a future where entire realities can be simulated down to the atom, or even below. Their reasons: scientific curiosity, historical reconstruction, entertainment, or even ethical research. Perhaps they simulate countless universes to see how intelligent life evolves. Maybe we're inside a university experiment in another dimension. Still, the simulation hypothesis raises objections. One of the biggest is the chaos computational complexity involved. Could even an advanced civilization store and process the data for every particle, thought, and interaction in the universe? Proponents argue that it wouldn't need to, just as a video game doesn't need to simulate the entire world at once. The simulation could be cleverly optimized, using procedural generation and predictive algorithms. And quantum uncertainty might not be a bug, but a feature built into the system. Others challenge the hypothesis on philosophical grounds. Even if simulations are possible, that doesn't mean they're inevitable. Advanced civilizations might have no interest in running ancestor simulations, or ethical concerns might prevent them from creating sentient suffering. Moreover, the hypothesis is difficult to test. If we are inside a simulation, the simulator could manipulate any observation or result. Any evidence we find could be fake. Any breakthrough could be reset. This makes the idea scientifically untestable, and therefore, some argue, meaningless. Yet researchers are trying. Some physicists have proposed searching for underlying discretization in space, like pixels in a digital image. If the universe has a minimum length, such as the Planck length, and time interval, that might suggest a grid-like simulation. Others look at cosmic rays, hypothesizing that a simulated universe might show directional patterns or energy limits based on the computational lattice used to build it. And yet, the most compelling question may not be, are we in a simulation? But, what difference does it make? If our universe behaves consistently, supports conscious experience, and follows discoverable rules, does it matter whether it's real or not? Does being simulated invalidate your emotions, your creativity, or your sense of wonder? Perhaps not. At Infinity Beyond, we see the simulation hypothesis as a powerful lens for exploring what reality truly is. Whether we're carbon-based life forms in a cosmic expanse or lines of code in an ultra-intelligent program, our experiences still matter. The questions we ask still have value, and perhaps the very act of wondering whether we're in a simulation is what makes us real, simulated or not. In our next episode, we'll return to something more measurable, exploring the fine-tuned laws of nature that make life possible. Are the constants of the universe designed, or a lucky accident? Subscribe now to Infinity Beyond. And let's keep questioning everything, even the nature of reality itself. Take a moment to consider how precisely our universe must operate for you to be watching this video right now. From the strength of gravity to the charge of the electron, the universe appears to be fine-tuned in a way that allows stars to shine, atoms to hold together, and life to emerge. But why is everything so perfectly balanced? This is the essence of the fine-tuning problem. The observation that the fundamental constants and physical laws of the universe seem to fall within incredibly narrow ranges that permit complex structures and living systems to exist. Let's look at a few examples. If the strong nuclear force, the force that holds atomic nuclei together, were just 2% stronger, hydrogen wouldn't exist. Stars wouldn't shine the way they do, and life as we know it would be impossible. If gravity were just slightly stronger, stars would burn out too quickly, and planets would collapse under their own weight. Slightly weaker, and stars might never form at all. Even the cosmological constant, which determines the expansion rate of the universe, appears to be fine-tuned to 1 part in 10 or 120. the most extreme precision known in physics. A slightly larger value would have prevented galaxies from forming. A slightly smaller one could have caused a rapid recollapse. Then there's the what ratio of matter to antimatter, the exact balance of electromagnetic strength, and even the mass of the neutron. Tiny deviations in these values would render a life-supporting universe completely unworkable. So, what's going on? Is this fine-tuning real? And if so, is it by chance, necessity, or design? There are three main schools of thought. 1. The anthropic principle. This idea suggests that we shouldn't be surprised the universe is fine-tuned for life, because if it weren't, we wouldn't be here to notice. In other words, life can only arise in universes where the conditions allow it. The weak anthropic principle simply states that our observations are biased. We see a life-permitting universe because we're alive in one. The strong anthropic principle takes it further, implying that the universe must have properties that permit life to develop at some point. Some interpret this as evidence for purpose, others see it as a selection bias. 2. The multiverse hypothesis. According to this view, there are countless universes, each with different values for fundamental constants. In this multiverse, most universes are sterile, chaotic, or empty. But in a tiny fraction, the conditions are just right for life. We just happen to live in one of those rare Goldilocks universes. This removes the need for a designer or a grand purpose. It's simply a game of cosmic odds. While this explanation satisfies many physicists, it comes with a major problem. We can't observe these other universes. They lie beyond our causal horizon, making the multiverse theory challenging to test. 3. The design hypothesis. This argument posits that the universe was intentionally structured to allow life, perhaps by a creator, an advanced intelligence, or even a simulated framework programmed to produce complexity. While this idea resonates with many philosophical and religious perspectives, it is difficult to quantify scientifically. It lies more in the realm of metaphysics than physics, but it cannot be completely ruled out. Some even propose that the fine-tuning we see might be a signal from the creators of the universe, perhaps built into the cosmic code itself. So where does this leave us? Some researchers explore mathematical inevitability, the possibility that the laws of physics couldn't have been otherwise, and the values we see arise naturally from deeper symmetries. Others search for grand unified theories, or string theory landscapes, that might explain why the constants take the values they do. But so far, no consensus exists. The fine-tuning debate touches not just physics, but of philosophy, theology, and existential reflection. Are we the product of a blind cosmic lottery, or are we meant to be here? And what if the universe isn't fine-tuned for life, but life is fine-tuned for the universe? In this view, life arises wherever conditions allow, adapting to whatever physics provides. This flips the question and sees evolution as a response, not a coincidence. At Infinity Beyond, we believe that exploring these questions is more important than settling them. The mystery of fine-tuning reminds us how precious and improbable our existence is. It challenges us to think big, beyond ourselves, and to appreciate the delicate balance that makes reality possible. In our next episode, we'll go even deeper, asking, is consciousness fundamental to the universe, or just a byproduct of biological processes? Subscribe to Infinity Beyond and join us as we question the origin of everything and the meaning behind it all. You're aware of these words. You're aware of yourself. But what is awareness? And could it be more than just a byproduct of biology? Some scientists and philosophers believe that consciousness may be more than an emergent property of the brain, that it might be fundamental to the very fabric of the universe. This idea may sound radical, but it's gaining traction in various fields of science. If true, it would require a profound shift in how we understand reality. Let's begin with the basics. In classical neuroscience, consciousness is thought to arise from complex interactions among neurons in the brain. Billions of cells, firing in coordinated patterns, somehow generate subjective experience, the feeling of I am. But this model doesn't explain how or why these patterns produce awareness. This is known as the hard problem of consciousness, coined by philosopher David Chalmers. Why does neural activity feel like anything at all? This has led some to consider more exotic possibilities. One idea is panpsychism, the notion that consciousness is a fundamental property of matter, like mass or charge. In this view, even electrons and quarks might possess rudimentary forms of experience. When arranged in complex structures, like brains, consciousness intensifies and becomes self-aware. Panpsychism doesn't mean your coffee mug is having deep thoughts, but it suggests that awareness might be a built-in feature of the universe, not something that just randomly appeared. Others propose the integrated information theory, IIT, which attempts to quantify consciousness as the amount of integrated information a system contains. According to IIT, consciousness is not all or nothing. It can exist on a spectrum. A rock has almost none, a brain has a lot, and a galaxy, maybe some. Now, let's turn the telescope around. What if instead of asking how the brain creates consciousness, we asked whether consciousness creates the universe? This might sound like mystical speculation, but quantum physics raises similar questions. In the famous Schwarzschild double-slit experiment, particles behave like waves until observed. The act of measurement appears to collapse their wave function into a definite state. Does consciousness cause this collapse? Some interpretations of quantum mechanics, like the von Neumann-Wigner interpretation, suggest that the observer plays a direct role in shaping physical outcomes. In this view, consciousness isn't passive. It actively participates in the creation of reality. Even physicist John Wheeler, one of the pioneers of quantum theory, proposed the participatory anthropic principle. According to Wheeler, observers are necessary components of the universe. Reality isn't fully formed until it's observed, and thus, in a way, the universe is self-aware. This leads us to the controversial idea of consciousness as fundamental, not emerging from matter, but the other way around. Could the physical world arise from a field of pure awareness? It's not just physics asking this. Mystical traditions from both East and West have long held that consciousness is the ground of being, the source of all manifestation. What if science is beginning to rediscover what ancient philosophies have intuited for millennia? The OR theory, developed by physicist Roger Penrose and anesthesiologist Stuart Hameroff, suggests that quantum processes within brain microtubules might be the seat of consciousness. While heavily debated, this model attempts to unify quantum physics and biology in a way that gives consciousness a central role in the universe. And here's the truly mind-bending possibility. If consciousness is fundamental, then perhaps it existed before the Big Bang. Perhaps the universe arose within consciousness, not the other way around. Could this explain why the laws of physics are comprehensible? Why mathematics maps so perfectly onto reality? Could it be that the universe is not a cold, random machine, but an unfolding pattern of awareness exploring itself? Some even speculate that the universe is a kind of self-simulating consciousness, a cosmic mind dreaming galaxies into being. If true, this would change everything. It would mean that consciousness is not confined to brains or biology. It could be everywhere, woven into the fabric of space-time, dark matter, even black holes. It might mean that you are not just in the universe is in you. Of course, these ideas are speculative, even controversial. Many scientists argue that consciousness can and will be fully explained by physical processes. The brain, in this view, is a machine made of meat. It produces thought, like a car engine produces noise, nothing more. But the truth is, we don't yet understand consciousness. We don't know how experience arises. We don't know why anything feels like anything. And that leaves room for wonder and for big questions. At Infinity Beyond, we believe those questions are worth asking. Whether consciousness is an emergent property or a universal force, it is the lens through which all reality is known. It's the most intimate and the most mysterious thing in existence. In the next episode, we'll shift from inner space back to outer space, exploring what might come after the end of the universe. Will time itself stop? Or will the cosmos begin anew? Subscribe to Infinity Beyond and join us as we explore not only what the universe is, but who is asking the question. Everything that has a beginning must have an end. But what does that mean for the universe and for time itself? The end of the universe is a topic that blends astrophysics, cosmology, and existential reflection. Will it collapse into itself, fade into darkness, tear itself apart? Each scenario paints a very different picture of the ultimate fate of all things. Let's start by understanding the universe's current trajectory. Thanks to observations of distant galaxies and Type Ia supernovae, we know the universe is expanding. And not just expanding, but accelerating in its expansion. Galaxies are rushing away from each other faster and faster, driven by an unseen force: dark energy. This expansion has profound implications for the future. One of the most widely accepted scenarios is called the Big Freeze, also known as heat death. In this model, the universe keeps expanding forever. As it stretches, galaxies move farther apart, stars burn out, and energy becomes evenly distributed. Over trillions of years, the universe cools to near absolute zero. No stars, no light, no motion, just a cold, dark void. Time would continue in this scenario, but everything meaningful within time would cease. But there are other possibilities. The Big Rip. In this more dramatic model, dark energy doesn't remain constant. It becomes stronger over time. Eventually, its repulsive force overcomes all other forces in the universe. First, galaxy clusters drift apart. Then galaxies themselves tear apart. Then solar systems, planets, even atoms. Space would stretch infinitely, and time itself could become meaningless. This rip would signal not just the end of structure, but the end of all information. Current data suggests we're not heading directly toward a big rip, but if dark energy evolves unpredictably, it's not off the table. The Big Crunch. This is the opposite of the Big Rip. Instead of expanding forever, gravity eventually halts the expansion and reverses it. Galaxies begin to fall back toward each other. The universe contracts, heats up, and eventually collapses into a dense, hot singularity, a mirror image of the Big Bang. This idea was more popular before the discovery of accelerating expansion, but some modified gravity models could still make it possible. If the universe ends this way, it might be cyclic, with a new universe bouncing out of the crunch. The Big Bounce. In this theory, the universe undergoes endless cycles of expansion and contraction. After each big crunch, a new Big Bang occurs, potentially with new physical laws or constants. This could align with ideas in loop quantum cosmology and even echo ancient philosophical views of eternal cycles. If the Big Bounce is real, we might be living in just one iteration of a multiverse carousel, and our cosmic story could be just one of infinite chapters. Vacuum decay. Here's a wild one. According to quantum field theory, the vacuum we live in might not be the most stable version possible. We could be living in a false vacuum with a more stable true vacuum waiting to be triggered. If that happens, a bubble of true vacuum could form somewhere in the universe and expand at the speed of light, erasing everything in its path instantly. No warning, no pain, just nothing. The probability is low, but the possibility is real. This scenario is linked to the Higgs field and potential energy states in the Standard Model of Physics. Now, let's take a moment to consider time itself. In these scenarios, time keeps ticking. But what if time isn't fundamental? What if time is an emergent property of entropy and order, something that only exists while there's structure, motion, and change? In a heat-death universe, where everything is evenly spread and no more work can be done, would time still have meaning? Without change, there is no before or after, only a frozen present. And if time ends, does it end for everything or just from our perspective? Some speculative theories suggest that new dimensions could emerge after the end of time, that a deeper substrate of reality might exist beyond space and time as we know it. In this view, the universe never truly dies. It transforms into something we cannot yet imagine. From a human perspective, these scenarios are overwhelming. The timescales involved, billions, trillions, even Google years, are far beyond our lives, or even the lifespan of our species. But contemplating the end helps us better understand the nature of beginnings, and it reminds us of something profound: impermanence. Everything we build, everything we know, even the stars themselves, are temporary. But in that temporary existence lies a kind of beauty. The universe is not static, it's dynamic, evolving, alive in a way. And we are part of that process. Perhaps the end is not something to fear, but something to marvel at, a final act in a cosmic story still being written. At Infinity Beyond, we explore these questions not to find all the answers, but to expand the space for wonder. Whether the universe ends in ice, fire, silence, or surprise, we are here now, aware, conscious, asking questions no other known species can. In our next episode, we'll look at what comes after endings, from rebirths in quantum cosmology to speculative ideas of what might exist beyond our universe. Subscribe to Infinity Beyond, and let's keep exploring, even the end. When you look up at the night sky, you're seeing just a fraction of the observable universe, a vast cosmic ocean stretching over 93 billion light-years across. But here's the mind-bending question: what lies beyond it? Does the universe go on forever? Is there a boundary, a wall, an edge? Or could there be something completely different? Another universe, another dimension, another everything? Let's begin by understanding what we mean when we say the universe. In cosmology, the observable universe is the region of space from which light has had time to reach us since the Big Bang, about 13.8 billion years ago. But because space itself has been expanding, this horizon extends far beyond 13.8 billion light-years. In fact, due to cosmic inflation, it's closer to 46.5 billion light-years in every direction. But the observable universe is not the whole universe. It's just the part we can see. Beyond that horizon, light hasn't had enough time to reach us yet. But that doesn't mean there's nothing there. Most cosmologists believe the universe continues far beyond what we can observe, potentially infinitely. But infinite in what way? There are a few possibilities. Infinite and unbounded space. In this scenario, space doesn't have an edge. No boundary, no wall, no outside. It just goes on forever, like the surface of a balloon, but in 3 dimensions. You can travel endlessly and never encounter a limit. This aligns with the Hall cosmological principle, which assumes that the universe is homogeneous and isotropic on large scales, the same everywhere and in all directions. But if the universe is truly infinite, then strange consequences follow. In an infinite space with a finite number of particle configurations, every possible arrangement of matter must occur somewhere, including exact duplicates of you, me, and even this video. Somewhere, in a region so distant it's forever unreachable, an identical Earth may exist. Maybe infinite Earths. This is the idea of the cosmic doppelganger, and it arises not from science fiction, but from mathematics, curved and finite space. Alternatively, the universe might be finite but unbounded, like the surface of a 4D hypersphere. In this case, space loops back on itself. If you traveled in a straight line long enough, you could, in theory, return to your starting point, though expansion would make this practically impossible. Evidence from the cosmic microwave background, CMB, suggests that space is very close to flat, but it doesn't completely rule out subtle curvature on scales larger than we can observe. Multiverse beyond the boundary. Here's where things get wild. According to inflationary cosmology, our universe may be just one bubble in a vast cosmic foam, a multiverse. During eternal inflation, quantum fluctuations give rise to countless bubble universes, each with different laws of physics, dimensions, and initial conditions. Our bubble expanded and cooled in just the right way to form stars, galaxies, and life. But other bubbles might be completely lifeless, or so alien that we can't even imagine them. In this view, beyond the universe doesn't mean empty space. It means other universes. Entirely separate realities, disconnected from ours by distance, dimensions, or causality. These bubble universes could be so far apart that no signal, no light, no gravity could ever bridge the gap. Yet their existence is mathematically implied by inflation models and supported by string theory's landscape of solutions, each corresponding to a different possible universe. Higher dimensions. Some theories, especially in tau string theory and brain cosmology, suggest that our entire universe might be a three-dimensional brain floating in a higher dimensional space called the bulk. In this picture, multiple brains, each a universe in itself, could exist side by side in higher dimensions, occasionally colliding or interacting. The Big Bang, in fact, might have been the result of such a collision, a burst of energy as two brains touched. If true, then beyond the universe literally means outside our dimensions, a place where different rules apply. Some even speculate that gravity is weaker than other forces because it leaks into these extra dimensions. Beyond physics? Perhaps the biggest mystery isn't what lies beyond space, but whether the question itself makes sense. Space and time might be emergent phenomena, arising from quantum entanglement or some deeper, pre-geometric reality. In that case, asking what's beyond the universe would be like asking what's north of the North Pole, a question that breaks down at a fundamental level. Yet the human mind resists limits. We are explorers, thinkers, creators. When we hit a wall, we build a door. And that's why the idea of beyond the universe captures our imagination. What lies beyond may not be reachable. It may not be knowable. But the pursuit of that question leads us to better theories, deeper science, and greater wonder. At Infinity Beyond, we're not just asking what's out there. We're asking why we care. Because in every question about the edge of the cosmos is also a question about the edge of our understanding. In our next episode, we'll turn inward again, exploring how time, space, and existence itself may arise from nothing. What does nothing really mean? And can something truly emerge from it? Subscribe to Eternity Beyond And let's continue stretching the limits of space, mind, and imagination. What if we erased everything? Every galaxy, every atom, every particle, every law of physics? What would remain? The answer seems obvious. Nothing. But the more scientists, philosophers, and cosmologists explore this idea, the more we realize that nothing might be one of the most complicated concepts in existence. In everyday language, nothing means a complete absence, a void. But in physics, nothingness is far from empty. And the question, why is there something rather than nothing, remains one of the most profound mysteries in science. Let's start with what modern physics tells us. In quantum field theory, empty space isn't truly empty, even in a perfect vacuum, where no matter exists and no light passes through. There are still quantum fluctuations. Tiny blips of energy appear and vanish in a fraction of a second. Particles and antiparticles pop into existence and annihilate each other. This seething foam of activity is called quantum vacuum energy. This nothing is actually something. It has measurable effects, like the Casimir effect, where two metal plates placed close together in a vacuum feel a tiny force pushing them together due to quantum energy differences. It even contributes to the expansion of the universe through dark energy. So from a scientific perspective, nothingness is never truly nothing. But what if we stripped away even quantum fields, space-time itself, the rules of physics, and even mathematics? Could we imagine a true, absolute nothing? Some philosophers argue that this state is logically incoherent. If there's no space, no time, no logic, no possibility, then the very concept of nothing collapses. Because to define nothing, we must use something, language, logic, thought. Others suggest that nothingness might be unstable. That is, perhaps nothing is not a permanent condition. If nothing is possible, then something could emerge from it simply because nothing prevents it from doing so. This idea is echoed in quantum cosmology, where entire universes could arise spontaneously from fluctuations in a quantum vacuum. This is the basis for one of the most exciting and debated ideas in theoretical physics. The universe could have created itself from nothing. Physicist Lawrence Krauss popularized this notion in his book, A Universe from Nothing, suggesting that the laws of quantum mechanics make it possible for entire universes to spontaneously pop into existence. According to this view, no external cause or creator is needed, just the laws of physics themselves. But critics point out a key issue. If the laws of physics exist before the universe, then that's not nothing, that's something. A background framework that allows reality to emerge. So maybe the real question isn't how something comes from nothing, but rather whether true nothingness is even possible. Religious and metaphysical views. Many religious and philosophical traditions also engage with the idea of nothingness. In some Eastern philosophies, emptiness is not a void, but a creative potential, the fertile ground from which all things arise. In the West, theologians have long debated the idea of creation ex nihilo, creation out of nothing, as a way to explain divine creation. But even here, the debate continues. Is nothing truly a starting point, or is it simply the absence of what we currently understand? Mathematical and logical nothing. In mathematics, the concept of zero was revolutionary. It allows us to define absence in a meaningful way, but zero is still a value. Similarly, the empty set is a defined object in set theory. It's not nothing, but a set that contains nothing. Even on null space, in linear algebra, is not truly nothing. It's a space defined by the solutions to an equation. We keep coming back to this. Every time we try to define nothing, we end up constructing something. So maybe the universe doesn't come from nothing. Maybe it comes from something we mistake as nothing. Cosmogenesis and space-time birth. In some cosmological models, space-time itself is an emergent property, not fundamental. For example, in all-loop quantum gravity, space-time is quantized and emerges from more basic, pre-geometric states. In string theory, the universe arises from vibrations on a multidimensional membrane, a kind of pre-space where conventional nothingness doesn't apply. Could our universe have tunneled from a previous state? From a non-being to being? If time doesn't exist before the Big Bang, then perhaps before has no meaning. This brings us to the concept of timeless creation, the idea that the universe's origin is not an event in time, but the emergence of time itself. So, what is nothing? The answer may be, we don't know, but that's okay. Because in asking what nothing is, we're really asking what everything is. We're confronting the edge of knowledge, where language, logic, and mathematics begin to falter, and wonder takes over. At infinity beyond, we believe that exploring the void isn't about darkness. It's about Oz depth. It's about staring into the abyss of the unknown and realizing that even the idea of nothing is richer than we ever imagined. In our next episode, we'll explore the origin of the laws of physics themselves. Where did they come from? Could they be different? Or are they written into the very essence of existence? Subscribe now to Peace Infinity Beyond and keep questioning. Even when the question is, what if there was never anything at all? The universe behaves in a remarkably consistent way. Apples fall, light bends, electrons repel each other. From the dance of galaxies to the flicker of atoms, everything follows a set of rules, the laws of physics. But here's a deeper question. Where did those rules come from? Why do they exist at all? Are they eternal, like divine truths? Or are they contingent, emerging only with our universe, and possibly different elsewhere? Understanding the origin of the laws of physics is not just an abstract curiosity, it may be the key to unlocking why anything exists at all. Let's begin with what we know. The laws of physics are mathematical relationships that describe how the universe behaves. These include Newton's laws of motion, Einstein's relativity, quantum mechanics, thermodynamics, and more. They allow us to predict how systems evolve, from falling apples to merging black holes. But here's what's strange. Why are these laws so precise, so elegant, so comprehensible? Option 1. The laws are discovered. Many scientists and philosophers, from Galileo to Einstein, believed that the laws of physics are discovered, not invented. That is, they are built into the fabric of reality itself, existing independently of us. We are like archaeologists, brushing away cosmic dust to reveal deeper truths. In this view, the universe operates like a giant machine, and we're slowly deciphering its blueprint. But that raises another question. Why this machine? Why not another? Why a universe governed by mathematics, rather than chaos or randomness? Option 2. The laws are emergent. Some physicists suggest that the laws of physics may be emergent properties, not fundamental truths, but outcomes of deeper, more abstract processes. For example, thermodynamics. The laws of heat and entropy emerge from the statistical behavior of countless particles. Similarly, space and time might emerge from quantum entanglement. Could the entire set of physical laws be emergent from something even more basic? This would mean the laws we see today are not fixed, but evolved, shaped by the conditions of our universe, like physical habits that formed after the Big Bang. In this scenario, the early universe might have explored many sets of physical laws before settling into a stable configuration, a kind of cosmic natural selection. Option 3. The multiverse perspective. If the multiverse is real, with countless universes bubbling into existence, each with its own physical constants, then the laws of physics may be local, not universal. We experience this particular set of laws because we exist in a universe that permits life. In another bubble universe, the speed of light might be different, or gravity might be repulsive. Those universes might be unstable, short-lived, or completely alien. This leads to an anthropic explanation. We observe these laws because only with these laws could observers like us arise. But critics argue this shifts explanation to chance, replacing wonder with statistics. Is there no deeper reason for the laws? Option Frau, the mathematical universe. Physicist Max Tegmark proposes that the universe is a mathematical structure, not just described by math, but made of math. In this radical view, every mathematically self-consistent structure exists as a universe. We happen to inhabit one that supports complexity and consciousness. The laws of physics are not imposed. They are the necessary truths of the mathematical structure we call home. This theory blurs the line between physics and pure math. But it raises another question. Why math? Why does abstract logic give rise to concrete reality? Option 5. The simulation hypothesis. Again, if our universe is a simulation, then the laws of physics might simply be all code. Programmed rules written by a higher intelligence. Like the laws in a video game. They may be arbitrary, tweakable, and even patchable. This brings us back to design, but not necessarily divine. In this view, the laws of physics are chosen parameters within a grand simulation engine. If we're in version 3.0 of the cosmos, who chose the constants? And could they be changed? Are laws really constant? Recent research suggests that some constants, like the fine structure constant, may vary slightly over cosmic time or across space. If confirmed, this would shatter the idea that the laws are immutable. It might also mean that we're catching the laws in the act of how evolving, like watching the rules of chess change mid-game. So maybe the laws are not fixed after all. Maybe they're fluid, responsive, or even creative in nature. Deeper still, are laws a human construct? Some philosophers argue that the laws of physics don't exist independently, that they are just our models to describe patterns we observe. The universe doesn't follow laws. It just is. We impose structure onto chaos to make sense of it. But if so, then how do our mathematical models work so well? As physicist Eugene Wigner asked, why is mathematics so unreasonably effective in the natural sciences? It's a question with no easy answer. At Infinity Beyond, we don't claim to know who or what wrote the laws of physics, but we believe the question is worth asking, not just to understand the cosmos, but to understand our place in it. Whether these laws were discovered, evolved, chosen, or created, they are what make the universe comprehensible. They allow us to build rockets, split atoms, measure black holes, and record thoughts like this one. And perhaps, in asking why the laws exist, we are glimpsing a level of reality even deeper than science has reached. In our next episode, we'll explore the strangest law of them all, entropy, and ask, why does everything tend toward disorder? And could entropy hold the key to time, consciousness, and the arrow of existence? Subscribe now to Infinity Beyond, and keep following the cosmic code wherever it leads. Why do castles crumble, stars burn out, and ice melt into water? Why does your coffee always go cold, but never spontaneously heat back up? The answer lies in one of the most profound and universal principles in physics: entropy. Entropy is a measure of disorder, or more precisely, the number of possible ways a system can be arranged. The more disordered the system, the higher its entropy. And according to the second law of thermodynamics, in any closed system, entropy can only stay the same or increase. This single principle underpins the direction of time, the evolution of the universe, and even the eventual fate of everything that exists. So, what exactly is entropy? Imagine a neatly stacked deck of cards. That's low entropy. There's only one way to arrange the deck so every card is in order. Now shuffle it. There are trillions of ways the deck could be scrambled, and each one is a higher entropy state. The same logic applies to atoms, molecules, and even galaxies. Entropy explains why heat flows from hot to cold, not the other way around. It's why gases spread out in a room instead of clustering in a corner, and why stars eventually run out of fuel. It's not that these processes are forbidden in reverse. They're just so incredibly unlikely. The number of high-entropy configurations vastly outnumbers the low-entropy ones. So statistically, the universe moves from order to disorder. Entropy and the arrow of time. Entropy gives time its direction, while the laws of physics are time-symmetric. They work the same forwards and backwards. Entropy introduces a distinction. The past is more ordered. The future is more chaotic. You remember yesterday because your brain formed memories in a lower entropy state. You don't remember tomorrow because it hasn't happened, and because entropy hasn't increased there yet. So in a very real sense, entropy is what makes time feel real. Without it, there would be no irreversible processes, no aging, no causality, and maybe no consciousness. Entropy and the early universe. The early universe was hot, dense, and surprisingly so ordered. This is strange, because high temperature usually means high entropy, but the early universe had extremely low gravitational entropy. Matter was spread out smoothly, like a calm pond. Over time, as gravity pulled matter into clumps, stars, galaxies, planets, entropy increased. That's why the universe can create structure. Even as it increases in entropy, local pockets of order, like life, can form as long as the overall entropy goes up. This is key. Entropy doesn't forbid complexity. In fact, it enables it. Entropy and life. You are an entropy machine. Your body takes in low entropy energy, food, sunlight, oxygen, and converts it into motion, thought, heat. Along the way, you produce high entropy waste, carbon dioxide, body heat, disorder. Life doesn't violate the second law. It runs on it. We maintain internal order by increasing entropy in our surroundings. Even your brain, with its thoughts, memories, and dreams, is powered by entropy flow. Some researchers believe consciousness itself may depend on entropy gradients, the flow of information through complex networks. Entropy and the end of everything. As the universe expands, entropy increases. Eventually, stars will burn out, black holes will evaporate, and matter will decay. What's left is a cold, dark, high-entropy cosmos, the so-called heat death. In this state, everything is maximally disordered. No more energy flows, no more processes, just a vast, silent equilibrium. In this future, time loses meaning. Without change, there is no before or after, only endless stillness. This is the ultimate consequence of entropy, a universe that winds down like a cosmic clock, ticking towards silence. Can entropy be reversed? No, in theory, entropy can decrease, but only with an input of energy and effort. A refrigerator, for example, reduces entropy inside by increasing it outside. Life does the same. But globally, entropy always increases. Some speculative ideas in physics, like entropy reversal after the Big Crunch, or Boltzmann brains, arising spontaneously in high-entropy vacuums, suggest that order can emerge even from chaos, albeit rarely and strangely. In the far future, new low-entropy regions might bubble into existence, perhaps even new universes. Entropy and information. In recent years, scientists have linked entropy with information. In fact, the formula for entropy in information theory is almost identical to the one in thermodynamics. This has led to radical ideas that the universe is not just made of matter and energy, but information. And entropy is a measure of missing information. Black holes, for example, have entropy proportional to their surface area, not volume. And Hawking radiation, which causes them to evaporate, is deeply tied to information theory. Could the universe itself be a giant or information processor, evolving through entropy? The beauty of entropy. At first glance, entropy seems sad, the slow march toward chaos. But it's also the reason we exist. Without entropy, there would be no change, no motion, no heat, no stars, no life. It is entropy that fuels evolution, drives creativity, and gives time its flow. Without it, the universe would be static, silent, and sterile. At infinity beyond, we don't fear entropy, we celebrate it. Because it means the universe is alive, moving, breathing, changing. And in the increasing entropy of the cosmos, we find meaning, fleeting, fragile, but magnificent. In our next episode, we'll ask a different kind of question. Could the universe itself be alive? What does it mean for a cosmos to be conscious, self-organizing, or even self-aware? Subscribe now to Infinity Beyond, and let's continue following the trail of entropy into evolution, emergence, and beyond. We often think of the universe as a vast, cold expanse, a cosmic machine governed by impersonal laws. But what if that's not the full story? What if the universe is not a dead, indifferent system, but something alive, a cosmic organism, pulsing with complexity, self-organization, and perhaps even awareness? It sounds like science fiction, but across physics, biology, information theory, and philosophy, a growing number of thinkers are revisiting the age-old idea of a living universe. Let's begin by asking, what do we mean by alive? Biologically, life is characterized by certain properties: self-organization, metabolism, adaptation, response to stimuli, growth, and reproduction. Traditionally, we've only applied these to cells, organisms, and ecosystems. But increasingly, scientists have noticed that the universe itself shares many of these traits. On scales far beyond biology, self-organization at every scale. From atoms to galaxies, the cosmos exhibits self-organization. Simple laws give rise to emergent complexity, like spiral galaxies, planetary systems, and even life. Clouds form patterns. Stars cluster into galaxies. Cosmic filaments stretch across the universe, forming a vast web that eerily resembles neuronal networks in the brain. Is this just visual coincidence, or something deeper? The Koch principle of emergence tells us that systems can display behaviors greater than the sum of their parts. Your brain is made of neurons, but your thoughts are not in any single neuron. They arise from interactions. Could our consciousness, or something like it, emerge from the vast interconnected structure of the cosmos? The universe processes information. Life is often defined by the ability to process information, to sense, store, and respond. The universe is filled with but information flow. Particles carry data, black holes store entropy, and physical laws behave like computational rules. In fact, some physicists describe the cosmos as a quantum computer, constantly calculating its own evolution. Theoretical physicist John Archibald Wheeler famously said, "It from bit," suggesting that everything arises from information. If so, then reality may be less like a machine and more like a thinking system. Gaia and the cosmic analogy. On Earth, the hot Gaia hypothesis proposes that the biosphere acts like a self-regulating organism, balancing temperature, oxygen, and ocean chemistry to sustain life. Could the universe operate in a similar way, with dark energy, matter, and entropy balancing each other in a form of cosmic homeostasis? Some go further, suggesting that the universe behaves like a complex adaptive system, one that evolves, repairs, and perhaps even replicates. Cosmic evolution. Life evolves. So does the universe. From the Big Bang to today, the universe has moved from simplicity to complexity. At first, there were only particles, then atoms, stars, galaxies, molecules, cells, organisms, minds. Each level of structure builds upon the last. This cosmic evolution doesn't prove the universe is alive, but it shows that the cosmos acts like a growing, developing being. From near-perfect symmetry, it has blossomed into stunning asymmetry and intricacy, much like life itself. The universe observing itself. Perhaps the most mysterious idea is this: you are made of the universe. Your brain, your thoughts, your questions, all constructed from atoms forged in ancient stars. And yet, here you are, observing the cosmos that made you. In this sense, the universe has become aware of itself, through you, through us, through consciousness. As Carl Sagan put it, we are a way for the cosmos to know itself. Could this feedback loop, where the universe creates observers who in turn observe the universe, be a kind of cosmic reflexivity? Is this the spark of cosmic sentience? Alternative theories and bold thinkers. Several thinkers have entertained these ideas. James Lovelock, originator of the Gaia hypothesis, suggesting Earth behaves as a living entity. Carl Jung proposed a collective unconscious that may be linked to a broader cosmic psyche. Teilhard de Chardin envisioned the universe evolving toward greater consciousness, a point he called the Omega point. David Bohm argued for an implicate order, a hidden, interconnected reality underlying the universe. Lee Smolin suggested cosmological natural selection, where universes reproduce through black holes, a form of cosmic evolution. Even all Hindu and Buddhist cosmologies have long spoken of the universe as a living, breathing entity, cyclic, conscious, and ever-transforming. Skepticism and scientific caution. Mainstream science remains cautious. Calling the universe alive risks anthropomorphizing, projecting human traits onto nature. Just because galaxies look like neurons doesn't mean they think like a brain. And yet, science also teaches us to follow the patterns. When different domains, physics, biology, information theory, begin to echo the same structures, we must pay attention. Even if the universe isn't alive in the traditional sense, perhaps it's alive in a new sense, one we're only beginning to understand. At Infinity Beyond, we believe the boundaries between disciplines and definitions are meant to be questioned. Maybe the universe is a machine. Maybe it's a simulation. Maybe it's a mind. Or maybe it's all of those things at once. In our next episode, we'll take one final step beyond the known, exploring the possibility that everything we know is just one layer of a larger hidden reality. Are we seeing the full picture or just the cosmic surface? Subscribe now to Why Infinity Beyond and join us as we continue this journey from chaos to consciousness, from entropy to emergence, and maybe from life to life beyond. Everything we've explored, the Big Bang, entropy, black holes, consciousness, the laws of physics, assumes one fundamental thing: that what we see is real. But what if it isn't? What if everything we think of as reality is just the surface layer, a thin projection of something deeper, hidden, more complex? This isn't mere speculation. Across physics, cosmology, mathematics, and philosophy, signs are emerging that the universe may not be what it seems. We might be living in a shadow of reality, like light flickering on the cave walls in Plato's allegory. Let's go deeper. The holographic principle. Let's start with one of the most astonishing ideas in theoretical physics, the holographic principle. According to this theory, all the information within a volume of space, say a galaxy, a planet, or even your body, could actually be encoded on a two-dimensional surface surrounding that region. In essence, the 3D universe we experience may be a projection from a lower dimensional boundary. Just like a hologram looks 3D but is made of flat data, reality might be holographic in nature. This idea isn't science fiction. It stems from deep studies of black hole thermodynamics, quantum gravity, and string theory. If true, then our very perception of depth and distance might be an illusion. Quantum weirdness, the collapse of objectivity. Quantum mechanics continues to challenge what we mean by real. Particles can exist in superpositions, multiple states at once, until measured. The famous double-slit experiment shows that particles act like waves when not observed, but become localized only when watched. It's as if observation itself creates reality. Some interpretations go further. The many worlds theory suggests that all possible outcomes do happen, just in separate branches of the multiverse. We only experience Other interpretations, like Cubism, argue that reality is fundamentally personal and only becomes real when an observer interacts with it. In short, quantum physics hints that there may be a no-objective universe, only a network of interactions and probabilities. Simulation hypothesis, reality as code. What if everything we see, from galaxies to grass, is not made of matter, but of information? This idea, championed by thinkers like Nick Bostrom and Elon Musk, proposes that we may be living in a simulation, a hyper-realistic program run by an advanced civilization. They point out that computers are getting exponentially more powerful. Simulations of entire worlds are becoming indistinguishable from reality. And eventually, simulated minds may outnumber real ones. If so, then statistically, we're more likely to be simulated than real. In this view, the hidden reality is the hardware, and we're the software. Mathematical reality, the universe as a structure. Mathematician Max Tegmark suggests that the universe doesn't just follow mathematical laws, it more is a mathematical object. Every consistent mathematical structure exists as its own universe. We inhabit one such structure, which happens to support consciousness and complexity. In this framework, reality is nothing more than a logical pattern. And the true nature of existence lies outside our physical senses. If reality is math, then what we see and touch are just representations of the underlying equations, filtered through the limitations of our perception. Consciousness and reality, a feedback loop. What if consciousness isn't just observing reality, but helping to generate it. Some physicists and philosophers suggest that mind may be more fundamental than matter, that consciousness could be the fabric of reality, not a byproduct. This would turn science inside out. Instead of a universe that produces observers, we'd have observers who produce the universe. A participatory cosmos. Could this explain why the universe appears fine-tuned for life, why physical laws work at all, and why quantum systems behave differently when observed? Are we dreaming reality into being? Ancient echoes, the veil of Maya. These ideas aren't new in Hindu philosophy. Reality is said to be Maya, a veil or illusion, hiding the deeper unity beneath. In Buddhism, all things are impermanent and empty of inherent existence. What we perceive is shaped by our mind. In Plato's philosophy, what we see are shadows, mere reflections of the true forms that exist beyond space and time. And today, physics is beginning to circle back, discovering that ancient intuitions about a hidden layer beneath appearances may have been right all along. So, what is real? Is reality physical, mathematical, informational, mental, simulated? Or is it something else entirely? Something we don't yet have the tools to comprehend? We may be like ants trying to understand a galaxy, sensing only what we need to survive, but missing the grander architecture that sustains us. At Infinity Beyond, we believe that humility is the first step toward wonder. Maybe we'll never know what reality truly is. Maybe it's not for us to see the engine behind the curtain. Or maybe, just maybe, we're on the verge of lifting the veil. One equation, one insight, one question at a time. Thank you for joining us through this journey. From the birth of the cosmos to the question of its meaning, from particles to purpose, from entropy to emergence. The universe is vast, mysterious, and wondrous, and we've only just begun. Subscribe to Infinity Beyond and keep asking the big questions, because the answers might be waiting just beyond the horizon.